So one way to interpret Gauss's law, or to deal with Gauss's law, is to consider a region of space that may be filled with a number of point charges. So consider a region of space that has, say, 4 positive charges. And let's go with, I can see it just fine. But would you like me to turn on the projector so you can see it? Charges, and let's say I also have 3 negative charges. And let's say that they are, we go with 5 coulombs, negative 3 coulombs, negative 2 coulombs, 3 coulombs, negative 5 coulombs, and let's go with 4 coulombs and 1 coulomb. Is there a surface that we can draw that would have 0 flux? Some kind of 3-dimensional surface that would have 0 flux in this region of space. Now, looking at it, I think the electric field in this region of space is probably complicated. I've randomly assigned the particles. I've randomly given them values. I don't know that we could easily predict the electric field here. Even if I was to measure it all out, it would be a complicated procedure to figure out the net electric field at that point from all of these charges that are there. But I can tell you right now that if it was part of a surface that wrapped around just these 2 charges, the net electric flux would be 0 because I've enclosed 0 charge. Electric field is not 0 at that point. In fact, I don't think the electric field is 0 anywhere on the surface. But I am guaranteed that the amount of flux going into this, the amount of field going into this surface and coming out of this surface must be equal. That is guaranteed by Gauss's law. Gauss's law is a law. It is invariant under all circumstances. Now, there's probably a variety of surfaces I could create that would have 0 flux, but are going to have a complicated electric field pattern. I mean, I see some right now, don't you? Like I could say, let's go with a green surface, this surface. 0 flux. Right? Has to be. Now, would this surface have 0 flux?
No.
How much flux would it have? If I solve this, so it's not 3, it'd be 3 over epsilon naught. That's how much flux it would have. Right? I just solved for flux, which is charge divided by the proportionality constant. That has to be how much flux there is. Does that tell you anything about the field? No, not really. I'm not sure it tells you anything about the field. What I'm trying to indicate to you is that Gauss's law has this interpretation. If you know the flux, you know the charge enclosed. That may be useful information. It may not be. But any closed and bounded surface that encloses a total charge of 0 will have a flux through its surface of 0. There's no way around that. But don't make it more complicated. That doesn't mean it tells you very much. Now, we could probably sit here for a while and find all sorts of combinations that would give us 0 flux. Or talk about questions like, well, if we have this surface, I don't have another color, so this surface, what's the flux there? Well, I could add it up, right? So 4 plus 1 is 5, minus 3 is 2. So this has got to have a flux of 2 over the permittivity constant. It has to be the amount of flux. Does that tell you much? No. It doesn't tell you very much. We don't know the area of that surface, and therefore we really can't understand what the electric field is at any point on that surface. I'm just stating the way in which the law operates. So are we good with this so far? This basic understanding, this basic idea of what Gauss's law is about. It's not about field. It's about flux. Go ahead.
I still don't understand why that 3C charge, I get the equation why it's not 0, but I can't get it, visually, why would that be 0?
I don't think it is 0.
The flux, I mean, why is net flux not zero? Why is the flux not zero? Because I thought if it goes out, like the direction of the area.
Well, first, if we isolated just this, like just your 3C charge, and that little red.
Through when you inbounded two different charges, like the.
Pick a color.
Oh wait, never mind. Now I see the charges all add up to zero. I see.
Now, go ahead.
So the only thing changing when you like change the surface is the area and the electric field. So as one gets bigger, the other gets smaller.
Yeah.
Okay.
Well, generally. Let me be really careful here, guys. Didn't bring up is looking back at this picture. The red surface, the flux is still 3 coulombs divided by epsilon naught. It would be true that it was 3 coulombs whether it was here with all of those other charges or a single. Why with all of these charges is it still just 3 coulombs over epsilon? All those other charges, although creating electric fields, the field lines pass into and out of that surface. So their contribution to the flux is 0. You see, the idea about flux here in Gauss's law is how many field lines originate or terminate inside your surface. They're the only ones that actually contribute to the flux. So if the field line didn't originate or terminate inside the surface, it's never contributing to the total flux on the surface. Any field lines that originated outside the surface have to enter and leave. And the only way they can terminate or originate is if there's a charge inside. That's the only way they can do so. Go ahead.
What do you mean terminate? Is that like 2 charges canceling each other?
Negative charges, field lines terminate because they point to the charge. And positive charges, electric field lines emanate because they point away from the charge. So by terminate, I don't mean like endpoints necessarily. I just mean that negative charges create electric fields that come towards them, and positive charges create electric fields that go away from them. Is that okay?
Yeah.
So don't read too much into the word originate or terminate there. Okay, only 5 minutes. So I want to get to some, so what is the usefulness of Gauss's law? Well, one of the problems with Gauss's law is when give me a second to draw something.
Okay.
So I have some charge located in space, isolated on its own, and the red lines represent the electric field around that charge. Right? If the point charge, we know we get this spherically symmetrical field around it, where the electric field is proportional to how far away you are squared, right? We know that from geometry and the fact we've looked at this before. So consider a Gaussian surface, and let's look at a symmetrical Gaussian surface. So I'm going to take a sphere and place it so that it's concentric with this charge. Now, I've been very careful about placing it concentric with the charge so that I can state to you the electric field is probably the same size everywhere on that surface. Are everybody following me so far? Because this part's critical. I want you to understand this. I don't want there to be any confusion. Now, if I take that same surface, make it smaller, I am now got a surface that is closer to the charge, so the electric field has gone up, but the surface area has gone down. And they must have done so in equal measure. Now, even this one, the electric field is the same everywhere around that surface, right? Because it's equal distant. Every part of that surface is an equal distance away from the charge. And we already know about Coulomb's law. So we know from Coulomb's law that the size of the electric field is proportional to how far away you are squared, or inversely proportional to how far away you are squared. Does the flux change if I move the surface over here? Have I changed the enclosed charge at all? Have I changed the flux at all? No. But I bet the electric field is stronger on parts of that surface than other parts of that surface. But the sum is still equal to the same value it was before.
The net electric field would be the same.
The net electric flux would be the same. I would never say net electric field unless I was adding up the contributions to the field at a single point. There's a lot of points that have all different electric fields here. And they're also going through the surface in different directions. So I would argue that it's probably got stronger, a stronger amount of electric field strength here and weaker over here. Okay so far? But the moment I take this surface and move it here, the flux is zero. There's no charge inside, so the flux is zero. But I still have charge lines going through it, so I know there's electric field here. The surface would have to register an electric field, but the electric field strength and the flux are different things. So in this case, I probably have some negative flux because some of the electric field is going into my region of space and some of my electric field is coming out of my region of space. All good so far? Now what you guys will point charge in space, if this was 3 coulombs, and I bring this little surface over, right, this is still going to have a flux of 3 coulombs over epsilon. Talked about, even though it's not obvious. Gauss's law is very difficult to use unless you can find a way to exploit the symmetry of a problem. Because just this question right here, what's staring us down right now, I don't think that we would have the mathematical skill to effectively calculate the flux outside of Gauss's law. What I mean is, you're going to be tricked. Is there a way, with what's pictured right now, using the math we know, to do this integral with this surface? And I don't know that there is. This is even a nice spherical surface. So I know a lot about the mathematics of a sphere. The problem is that, look, those field lines are all different angles. Right? Every single one of them is going through that surface at a different angle. And they're all different amounts. Some are close to the charge, some are far away from the charge. I think this would be nearly impossible. On the other hand, a carefully drawn or a carefully selected surface might have certain symmetries that might allow us to calculate the flux. Like if I just take that surface, knowing that it's symmetrical, and place it so that it's concentric with the charge, like I've done, then suddenly every one of these points where the electric field passes through the surface all pass through that surface at the same angle. Right? They're all the same. In fact, more than that, they're all 0 degrees because the direction of the area at each of these points points away from the center because it's a sphere. That suddenly means I have a certain amount of symmetry that I might be able to exploit to calculate the flux directly without using Gauss's law. Everybody following so far? A little bit? This part's where it's going to get hard because we're going to have to use Gauss's law to be able to calculate flux 2 different ways. One of them is by using the law as stated, as we just looked at. One of them is by finding a way to choose a carefully constructed Gaussian surface that has exploitable symmetry that allows me to actually mathematically calculate or execute this integral. With our goal being not to figure out the flux, but our goal being to use Gauss's law to figure out the electric field. That's what we're going to try and do. What I would like to find a way to do is use Gauss's law in a manner that's not necessarily consistent with its goal of showing how flux and charge are related, but to use it to find what the electric field is for certain kinds of situations, and this is one of them. Consider this situation. If I just wanted to calculate the flux, can we agree that every point here is the same distance away from the charge at the center? We know from prior experience that that means the electric field is the same strength at every one of those points, making in this calculation E a constant. Now, if we've done integrals before, we know one thing about constants in an integral. They pass outside the integral because every term has the same value as a constant. So let's consider what we might be able to do if we're careful about constructing our surface. First, going back to this, the electric field. I do think it's a constant, but also I believe the direction of the field with respect to the surface is 0. So I'm going to take away the dot product and put the cosine of 0 degrees in there. And then that leaves me with dA. Now, if E is a constant, then it passes outside of the integral. Right? We all good so far? Well, all that's left is something that says to sum up the entire area of a sphere. What is the area of a sphere? Excellent. Where r squared represents this value for r, right? Okay, I know I'm holding you, but just watch. In Gauss's law, that has to equal the charge enclosed, correct? If I solve this for E, I get Q enclosed over 4 pi epsilon naught times r squared. Correct? In fact, we define K as 1 over 4 pi epsilon naught, making this QK over r squared. So Gauss's law proves Coulomb's law. All right, have a nice day. If I had just a point charge that was 3c and some not symmetrical, surface around it. So I'm not even including what's around the outside, just this. Then this particular surface encloses 3 coulombs of charge. Gauss's law is a law, regardless of what's around it. Gauss's law states that the flux through any closed and bounded surface has to be equal to the total enclosed charge divided by the proportionality constant. You don't have to understand why that's true. It is true. It's a law. I drop the ball, it falls to the ground. It's a law. You don't have to understand why it does it, but it's true. It's a law. Now, what this probably means is that the total amount of electric field emanated from this charge, combined with the area of this surface, would give a flux equal to 3c over epsilon naught. But this surface would have the same flux passing through it, as would this surface. They all must have the same flux passing through them because they all enclose the same amount of charge.
Why was it different with the two charges in one?
What's that?
Like, why was it different with the